Reliable battery management requires predicting the internal electrochemical state of a lithium-ion cell without the ability to measure that state directly. To bridge this inference gap, researchers use simulation frameworks to model specific hardware configurations. In this case, a multi-cell pack arranged with 4 cells in series and 3 strings in parallel, known as a 4S3P configuration. This specific pack is subjected to 4 distinct constant current discharge scenarios: 0.5 amps, 1.0 amps, 1.5 amps, and 2.0 amps. By sweeping across these discrete load levels over a precise 1-hour interval, we can track exactly how current magnitude influences terminal voltage sag, state of charge depletion, and the resulting thermal rise. Quantifying the link between current intensity and the internal state of the battery establishes the foundation for designing more robust, load-aware BMS control architectures. To ensure the results are fully reproducible, the simulation is bounded by a strict environment in MATLAB R2023B. Each 1-hour test produces exactly 3,600 updates at a 1-second time step, always starting from a 100% state of charge with uniform pack parameters. The model calculates terminal voltage by subtracting resistive loss from nominal voltage. State of charge uses a Coulomb counting algorithm, integrating current over time. A nonlinear correction model also accounts for SOC-dependent resistance variations, providing a sensitive reference for benchmarking. Locking in these mathematically defined parameters eliminates structural bias, creating a stable reference for evaluating how load severity specifically induces estimation error. This chart shows the voltage, state of charge, and thermal profiles at the lowest load setting of 0.5 amps. Over the 1-hour interval, the voltage curve remains close to the nominal level, with minimal thermal rise. At 1.0 amp, the state of charge in the middle pane tracks a linear decline. This reflects the direct, proportional relationship between the discharge current and the rate of capacity withdrawal. Examining the 1.5 amp load reveals a clear change in the trajectory slopes. As the demand increases, both voltage and state of charge decline at a noticeably faster rate. At the maximum 2.0 amp load, initial voltage sag is much sharper, directly resulting from intensified I²R losses. After 1 hour, final capacity levels clearly show the impact. The 0.5 amp run finishes at 94% capacity, while 2.0 amps reaches just 76%. These trajectories confirm that higher discharge currents predictably extract capacity, but they also significantly shrink the usable voltage margin required for stable power processing in converter-based systems. This chart tracks the cumulative electrical energy delivered by the pack. Because the currents are fixed, the energy delivery scales linearly, rising from 6.6 watt-hours at 0.5 amps to exactly 26.3 watt-hours at the 2.0 amp limit. However, internal heating losses are driven by the I²R dependency of resistive heating. At 0.5 amps, heating loss is a negligible 0.003 thermal watt-hours. At 2.0 amps, it reaches 0.056 watt-hours, following a clear quadratic growth trend. This demonstrates a sharp trade-off. A 4-fold increase in load current yields a 4-fold increase in energy output, but induces a 19-fold increase in thermal stress. This disproportionate rise in heat relative to energy delivered confirms that thermal efficiency drops substantially as load currents increase. Comparing the results at the 1-hour cutoff highlights the difference between runtime and temperature. While the runtime is identical across all tests, the temperature rise scales aggressively with the load. The increment grows from just 0.03 degrees Celsius at the lowest load to 0.56 degrees at the 2.0 amp peak. Mapping temperature against state of charge reveals how joule heating accumulates. The curves show a sharp initial rise early in discharge, confirming resistive heating is prominent before internal temperatures stabilize. Eventually, the curves flatten as heating tapers off, and the pack approaches thermal equilibrium. Although this 4S3P pack remains thermally comfortable under these modest currents, the 19-fold escalation in heat indicates how quickly stress compounds. This nonlinear relationship establishes the need for load-aware thermal safeguarding within BMS protection logic. This chart presents the joint evolution of pack temperature and terminal voltage. As discharge progresses, trajectories move right to left, mapping the steady voltage decline. temperature rises more gradually, causing curves to hook upwards later, as seen in the 2.0 amp vertical ascent. A key observation here is that voltage deterioration manifests earlier and far more distinctly than the upward rise in thermal data. This makes voltage-based early warning indicators a highly effective tool for preventive control, allowing the BMS to respond to excessive load conditions before critical thermal thresholds are reached. The consolidated data at the 1-hour cutoff confirms the electrical and thermal behavior of the 4S pack. Load severity dictates both usable energy and structural stress. The 2.0 amp run delivers 26.3 watt-hours, but incurs the maximum 0.56 degree temperature rise. Managing a multi-cell pack requires balancing power demands against narrowing voltage windows, while enforcing the thermal safeguarding protocols necessary to preserve long-term pack integrity. For MATLAB simulation works, battery modeling, BMS studies, SOC estimation, and research coding support, contact creativepublications2020@gmail.com.